Hi everyone. In today's video, we will start our discussion on various optimizers used while performing the backpropagation step to update the weights in neural networks. In this particular video, we will be discussing in detail about the structure of the most basic optimization algorithm, which is the gradient descent. We all know the updation rule of gradient descent algorithm by now, or at least you have an idea on how a gradient descent rule works. So let's say we know weights at time t. The weights at time t plus 1 should be equal to wt minus alpha times gradient of loss with respect to wt. So this is the gradient of the loss. So L is actually a loss function which we will be defining, and the weights at that particular time t, it is taken into consideration alpha, or in many cases it's written as eta as well. This is, in either cases, this is the learning rate, and this is determined before we start the gradient descent iteration process, and we successively update the weights in this way. We, however, will like to discover why exactly the gradient descent rule is written in this way. In doing so, we will derive how the updation rule was found and how exactly we can use linear algebra to find the optimal learning rate subject to the loss function under consideration. The video is going to be a bit heavy in terms of mathematics used, as we will be using linear algebra concepts and some calculus concepts which you may have studied in some basic mathematics course till now. We will first try to consider a basic numerical loss function in one dimension as shown below. So this is the loss function which we are having. LW is the loss function. The gradient of L with respect to W is the first derivative with respect to W, which is L dash W, which is written over here. It is nothing but derivative of LW, which is 8W minus 12. The double derivative is written over here. Now, if we see intuitively, the solution to this problem could easily be found out by considering the derivative and equating to 0, which will give me the answer of W to be 1.5. But we will start with an initial value of W naught, a value of eta, which is 0.2, and follow the gradient updation rule of the gradient descent algorithm. So this is the gradient updation rule of the gradient descent algorithm. We know that the gradient of L with respect to t is given as 8 times Wt minus 12. Wt will be known in some way, and once we know it, we will be using this updation rule to update the value of W in successive iteration. Here k refers to the number of steps. So we do calculations in Microsoft Excel. We won't be using any programming language here for this simple example to keep the understanding simple. So here it goes. We start with the value of W as 3. This is the value of W which we are getting after gradient updation rule. And if we consider the gradient updation rule which we did previously, it looks like this. Now we have the value of W we start with. This is the value at time 1. We successively iterate, and this is the loss we are getting. Now based on this value, we are able to obtain a value which is present over here. Just keep a track on the updation rule which I am mentioning over here, and also the formula which I am applying. And successively we keep on applying, and at one point of time we kind of reach a point where the losses are very less, and the loss function is very much trivial, which we defined over here. This was the loss function which we were trying to minimize, and at one point of time we are getting losses near to zero, and this is exactly happening when we have reached somewhere around 1.5, which was the answer. So this is how the gradient descent algorithm works, subject to the learning rate selection and also the initial weight selection, which we showed over here. We will proceed forward to know how it is working. We will use a basic approximation that we learned in our calculus called as the Taylor series expansion. So we have a function fx, and it is differentiable at a point A. the expansion of fx in terms of a is given as this. So fx is fa plus f dash a by 1 factorial x minus a, f double dash a by 2 factorial x minus a square, and so on. So now we make one substitution. The substitution works like this. We will replace the loss function f with L, and we will replace the value of a with wk and the value of x with wk plus 1. Now on doing so, we get an expression which looks like this. So we have loss at weight wk plus 1, which is equal to loss at wk L dash wk by 1 factorial. Since we replaced x with wk plus 1 as we discussed, we do that. And everywhere, wherever a is coming, we replace it with wk. And on doing so, this is the approximation we are getting. Now we make an assumption that the loss function is quadratic in a specified bounded interval where the Taylor's theorem is applicable. Here we ignore all the terms above degree 2. In the expression, we get the equation of LWK plus 1 as because we know only till WK, we don't know WK plus 1. We proceed forward to partially differentiate this equation L of WK plus 1 with respect to WK plus 1, and we get this. So we have LWK plus 1 and we differentiate with respect to WK plus 1. The first term gets differentiated, this LWK gets differentiated over here. This is a constant. Even though we are differentiating just to make the calculations a bit clear, but this is actually a constant which we won't be differentiating, as you will see in successive steps. It will come out like here. We just have to differentiate wk plus 1 minus wk, which we are doing over here. Likewise, L double derivative of wk by 2 will be used as a constant, and whatever remains inside this expression will be differentiated, and we will apply the derivative over here. We solve further, and this is what we get. L dash wk we have, because wk plus 1 minus wk, if we are differentiating with respect to d by dwk plus 1, this entirely gets cancelled and is equal to 1. L double dash wk by 2 will be used as it is, and this term resolves to twice of wk plus 1 minus wk, which we are writing over here. And on solving further, both this 2 and 2 gets cancelled, and this is the eventual derivative we get. Now we need to find the value of wk, and hence we will be looking forward to equate this derivative to 0. On doing so, this is what we are getting, and pretty much we get the result from here only. We take the equation from here. This is the equation we were having. Equate it to 0. So the first thing is this L dash wk goes to the RHS. Since wk plus 1 minus wk was multiplied by this term goes over here in the denominator, and the minus of wk goes to RHS, and this is how we are getting the final result. We rewrite with the fact that eta could be written as L double derivative of wk, and this is actually the learning rate which we are considering, and this is exactly how we get the gradient updation rule. Now we proceed further to calculate the double derivative, and we get the double derivative to be greater than 0. Now wk plus 1 is the local minima, and this is the local minima of the loss function which we have considered. Now also we were able to make an assumption that the value of learning rate is equal to 1 upon L double derivative of wk. All these things we were able to do in a scenario where we are dealing with only one variable. So just to recap, we did this. So we started with the Taylor series expansion. We imputed the value of f with the loss function. Wherever the value of x was there, because x was unknown, we replaced it with wk plus 1. What was known is being taken in place of a, wk is being taken in place of a. We rewrite the entire expression, and we make a strong assumption that the loss function in any bounded region where we will apply the Taylor series approximation is a quadratic function, and hence we ignore all the terms above the degree of 2 from the expression. This is what we get. And then since we need to find wk plus 1, we differentiate with respect to wk plus 1. We solve a bit, and for extremum points, just like we do in calculus, we equate the derivative to 0 and get the final updation rule. Now we need to make sure this updation rule is minimizing the loss function. That's what we do. We do the double derivative, which is greater than 0, and hence we get the local minima. And the local minima is obtained when we do an updation rule like this. However, we may need to consider more than one dimension, and in such cases we will consider the multivariate Taylor series approximation method. So in multivariate case, we will proceed with some assumptions. We will say that the derivative of L with respect to Wk is the gradient of L with respect to Wk, which could be written as G. The double derivative could be written in the form of a Hessian matrix. Also, we can write this entire term, which was due to the fact that we are assuming the loss function to be quadratic in the given interval, in this form. So just to tell you, Wk is a vector and H is a matrix. So in vector, we can't write something like this, Wk plus 1 minus Wk square. We always have to write it in the form of a transpose. Just that when you write dot product, you always say the dot product of A with itself is A transpose A. We don't write that A vector whole square. Like in the same way, we proceed and write the expression of double derivative like this. We use the same set of assumptions and make the replacements appropriately. We put LWK as it is. The double derivative is being put over here. So this entire term this entire term was actually Wk plus 1 minus Wk square, and then L double derivative of Wk, and the 2 was there of course, and this entire term Wk plus 1 transpose into G, this entire term was once Wk plus 1 minus Wk into L dash Wk. So all these things, this term as well as this term, is the one-dimensional equivalent of the multivariate situation which we are discussing over here. And we found it easy to first derive for the univariate case as we did previously. Then we proceeded with the multivariate scenario because it helps in the understanding easy. Because we knew that at one point of time, if we are able to consider a univariate case and do the derivative, we can get the result. We can get some form of learning rate which is dependent on the double derivative. Now we want to see how exactly that maps to the multivariate scenario which we are having. Now we proceed further, do the same thing as we did previously and partially differentiate with respect to Wk plus 1. The first term will vanish because gradient of LWk, and this gradient is done with respect to Wk plus 1, will be 0 because there is no term dependent on Wk plus 1 present over here. So this term will be 0. This term, the second term, will be differentiated and the only thing left will be the gradient part. We will get the Hessian and Wk plus 1 minus Wk. So this is what we are proposing in the solution as well. So this is the reason why we are getting the derivative of L with respect to Wk plus 1 as something like this. Like we did previously, we equate the gradient which we have obtained over here to 0, and on doing so, we get a term like this. Now let's solve it a bit carefully because we are in a multivariate case and we are dealing with vectors and matrices. We need to solve this equation in a proper way. So this is what we are getting. We take the G to RHS with a negative sign. H is a matrix which is being multiplied with the difference of two vectors. We pre-multiply with H inverse and we get this. Now on solving further, we get equation in terms which will be looking like this. So we got the final updation rule, which looks like this. We got the gradient of LWK, just like as we got L dash WK in the previous setup for the univariate case. We got the previous weights as well. Over there, the double derivative 1 upon L double dash WK was being considered as a learning rate. Now this is a scalar over here. Now we are getting learning rate equivalent to H minus, which is a matrix. We can clearly see an issue over here. We need to find the inverse of Hessian, but if we have a large number of variables to optimize, we may end up getting a Hessian of a significantly higher dimension, and we may not be in a position to calculate the inverse of H in computationally less expensive ways. Also, we may end up with a Hessian that is approximately singular. In such cases, we need to replace the H inverse with a learning rate eta. This is the learning rate, which is scalar. Now, this is a big substitution we are going to make over here. Also, there is a lot of candidates for eta. Eta can take any values. If we are selecting a scalar variable in place of a matrix multiplication happening, there are a lot of values it can take. We need to pick up the one that gives the best result. In other words, we need to pick up the eta, which not only helps us in convergence of the loss function, but also does the convergence in a finite number of steps. We do this in the following way. We take a note of the fact that wk plus 1 could be represented like this based on the updation rule we have determined previously, with the only thing that we want a scalar eta to substitute H inverse. We take the expression of LWK plus 1 as we have derived previously and substitute the value of WK plus 1 using this assumption in the expression. Over here, we can clearly see that at this point of time, we just have only one unknown term, which is the eta. So we know WK, we know that WK plus 1 could be expressed in the form of WK. We established this relationship previously. We know WK at time K plus 1. And now we proceed further and we get the results like this. So we consider the term WK plus 1 minus WK first. Now if we just solve WK plus 1 minus WK, we put this substitution over here. We are only left with minus of eta gradient of LWK. We are going to put the same thing over here and we replace it with the fact that gradient of LWK could be written as G. So we say that the transpose of this term is eta times G transpose. We have derivative of LWK as G. We write it over here. We take the term WK plus 1 minus WK transpose as it was shown over here. It was eta G transpose H. We get the value of H as it is. And on solving this, we get eta G. Both the negative term get cancelled. We get the term which is positive, and the final result comes out to be this. Now in this entire expression which we have solved till now, the unknown term is eta only, which we need to determine and we need to minimize to find the optimal value of eta. Now we partially differentiate with respect to eta. This first term gets cancelled out because this is a constant term independent of eta. We get G transpose G over here and eta square will be 2 eta, 2 and 2 gets cancelled. This is the final term which we are getting. Now for extremum points, we equate this derivative to 0 and the final equation of eta or the learning rate comes out to be this. Here also we need to find the value of H, which is computationally expensive. So there is a workaround which we can do. So this is what we do. So since H is a symmetric matrix because Hessian is symmetric, we use the eigen decomposition theorem over here to decompose it in the form of QD Q transpose. This is the eigen decomposition theorem, where the value of D or the matrix D is a diagonal matrix consisting of the eigenvalues and Q is the eigenvector matrix which we have. We substitute it in G transpose Hg, and G transpose Hg was actually a term which we obtained in the denominator. We start with it and say that Q transpose G is equal to X. We get a term like this. Now we have X transpose dx, where D is a diagonal matrix. On solving, we get a term like this. So this is simple matrix multiplication when the middle matrix is a diagonal matrix, and X transpose and X are ideally going to be the sum of the terms which are there in the matrix multiplied with the eigenvalues. Eigenvalues are present in the diagonal matrix. We say that out of all the eigenvalues present, lambda max is the maximum eigenvalue which we are having. On doing so, we proceed further and get a result like this. So we know that lambda is less than lambda max because lambda max is the maximum eigenvalue. We multiply with xi square because xi square is greater than 0 and the inequalities won't change. We do the summation across all the terms over here. On doing so, lambda max will come out because this is a constant term, and we are left with this final expression over here. Now we will take advantage of one important property of H, which is the fact that it was symmetric. Again, if H is a symmetric matrix, all the eigenvectors which form the matrix will make the matrix Q as an orthogonal matrix. And for an orthogonal matrix, Q transpose Q is equal to Q into Q transpose is equal to I. We can pre-multiply both the sides with G transpose and get this. And now, yeah, G transpose. And we post multiply with G to get this. So now we substitute G transpose QQ transpose, which we were able to find, and this term is happening only because we have made X transpose dx over here. Summation xi could be expressed in the form of X transpose X only. Now we replace a term with the substitution we have made for X. The value of X was Q transpose G over here. So we replace with Q transpose G. X transpose becomes G transpose Q into Q transpose G, which is from X. We do this substitution basically. X is equal to Q transpose G. That's it. Now, since this is orthogonal, Q is orthogonal, QQ transpose will be 1. We end up with G transpose G. We divide both the sides with G transpose Hg, and eventually we get a relationship which looks like this. Now if we scroll up a bit, this was actually the value of eta which we were able to find out on equating the derivative to 0. Now this proves that eta can no doubt take any value because it is a scalar, but for convergence to happen, it should be at least equal to 1 upon lambda max, or 1 upon highest eigenvalue of H. So let's recap a bit on how we proceeded with the multivariate case. So we knew that for the univariate case, the derivative of L with respect to K was L dash WK, and this was a double derivative. We replaced the univariate derivative with gradients and Hessians. We considered few terms, WK plus 1 minus WK, and then we made an attempt to replace it with the corresponding assumptions we just made over here, and then we partially differentiate the term with respect to WK plus 1. On doing so, we get the derivative of L with respect to WK plus 1 as this. We proceeded further for extremum points to get the update rule, which looks like this. Now it had a caveat that H inverse needs to be calculated, which in many cases may be not possible because it's computationally very expensive and also the matrix may be singular, and hence we proceeded with finding one scalar term eta which could be used in place of H inverse. Now we don't know what this eta is, but we definitely know what the gradient updation rule which we were able to find out previously. We proceeded with applying the assumption that H inverse is to be replaced with eta. We considered the same formula of LWK plus 1 and proceeded further. We get a term like this, and then we partially differentiate with respect to eta, and for extremum points we were able to get the value of eta to be equal to this. Now this had a caveat that H needs to be found out, which is computationally expensive each time we work. So we use the eigen decomposition theorem where the Q is the eigenvector of the matrix and D is the diagonal matrix whose diagonal entries are eigenvalues. We proceed further, make an assumption that X is Q transpose G, and this is actually a very important assumption which will come much later. We find out the maximum eigenvalue, multiply both sides by xi square, and then conclude that summation xi square is equal to x transpose x over here, and then use some properties of eigenvectors of a symmetric matrix. The eigenvectors of symmetric matrix are orthogonal, and on solving a bit further, and eventually we are able to get the lower bound of the learning rate, which looks like this. Calculating. On doing so, we can see one thing over here. The loss is getting reduced, and at one point of time we are getting the minimum loss, which is happening when both W1 and W2 are close to 1. Now if we see the equation carefully over here, this was the equation. Now if I have to solve it by observation only, the optimal value of W1 and W2 should be 1 only, and on doing so the loss should be equal to 7. Now since we were able to get the learning rate as 1 by 6 optimal learning rate, we were able to get convergence in finite number of steps. Now we will consider two scenarios where the value of learning rate which we are selecting over here, we will start with the same value of W1, but we will start with different learning rates and see whether we are able to converge or not. We start with eta equal to 0.05 and we get the value of W1 and W2 iteratively if we calculate, because when we selected the learning rate 1 by 6 over here, we were able to get a better form in terms like this, which was a compact form. Now since we are changing the learning rate to 0.05, we have to recalculate both W1k plus 1 and W2k plus 1, which on doing mathematically, these are just the mathematical terms which you can do with different values of eta. We get different values of W1 and W2 and the corresponding loss function. Just observe, we are yet not getting a convergence in finite number of steps. So we were able to get close to 7 but not exactly 7. We are getting values close to 1 but not exactly 1. Now if we see why exactly this is happening, it's because of the fact that we selected the value of eta as 0.05 while the optimal value of eta was 0.16. So we selected the value of learning rate much less than the optimal learning rate. Hence, in some finite number of steps, we were not able to get a convergence. We could get a convergence much later, but if we had selected the learning rate as 0.167 or 1 by 6, we could get a clear convergence in much less steps. While over here, in the exact number of steps, we are not getting a convergence at all. Now let's see what the bound actually told us, that the optimal value of eta should be greater than 1 upon lambda max. That is, the optimal value of eta could be greater than 1 by 6. We selected one eta which is equivalent to 0.3. On doing so, we can see that our calculation gives us convergence in even lesser number of steps. We are getting convergence in around say 6 to 7 iterations. So we actually got a bound for the lower limit of learning rate we need to take to get the finite number of steps for convergence. So in this video, we were able to do two things. First, we were able to find out the gradient updation rule when we talk about a gradient descent algorithm, and also how to find out the optimal learning rate when we are dealing with multivariate case, or in other words, optimal learning rate when the number of weights are greater than 1. In the next video, we will be discussing about some of the variants of gradient descent algorithm like resilient prop, momentum gradient descent, or Nesterov accelerated gradient descent, which serve as further enhancements of gradient descent algorithm and give much better results in much lesser number of steps. Thanks for your time.